begin quickly. What we're going to talk about today is a little bit about reservoir operation, what is the current practice, and what we should expect to see in the future, both in terms of flood management and drought management. And I want to touch upon the flood design estimates and also the current practices in India and how it could possibly be improved. Let's begin by reviewing what most of you know here. The reservoir operators are currently assisted by these two lines, which are called the upper rule curve and the lower rule curve. And both of those lines are developed typically using trial and error. The upper rule curve requires that we increase the flood storage zone occasionally on some reservoirs where that is necessary. The lower rule curve prevents us from emptying the reservoir storage too soon. So what we do now is we use all sorts of simulation models, trial and error. We put different curves in, then we look at the output, and that may be fine for a single reservoir system, but when you have many reservoirs and many users, it becomes rather cumbersome and the output is very uncertain. In fact, the output often depends more on the user than the kind of model you're using. Do the rule curves really help reservoir operators all that much? Well, if you're an operator, this is the current level that I'm showing. All the lower rule curve will tell you is what should be the level that you shouldn't go under in the next 10 days, if it's a 10-day time step decision. It doesn't really tell you where you should be, it doesn't tell you how much to release. So it's essentially, what I'm trying to say with this slide is that we really are operating the reservoirs as reservoir operators. We don't get that much help from technology these days. If you were an operator and you were operating a reservoir during a high flow season and you're releasing, say, flow which has a stream velocity of 2 meters per second, and this is a very important slide, how far will this release reach? It'll reach about 43 kilometers downstream. And you know that most basins are much bigger than 43 kilometers. So what we are going to have to do is see what happens to it after the release. Of course, this release will attenuate. There will be some tributaries along the way, which may increase it to this dashed line. And then you'll have another attenuation. And this, but by the way, is the area that we're trying to protect from flooding. We have not connected the release in this first 6-hour time step to the damage that may happen 18 or 24 hours later. And this is a problem both for simulation models and for reservoir operators in real life. We do need to know what is the full bank capacity downstream in order to know what our target is. But this target is not linked in any single time step solutions with the release. The reason for this is that we have the attenuation, and we're also not taking into account more than one time step at a time in most models, and simulation models are the norm. So we have inflow here, and we have initial storage, and what you see is this dashed line, which essentially is the ending storage at the end of time step. If we copy this system and make this ending storage automatically become the starting storage for the next time step, and we do it for all time steps for which we have the time horizon of forecasts, then we are going to create this so-called multiple time step optimization. What this will do is it will give us a perfect reservoir trajectory. In other words, it will give us a perfect rule curve given the starting storage level and the water demands. And we do need forecast for this, and we do need to solve this so-called dynamic network. Now, none of the simulation models are capable of doing this. So the future is not simulation or improved simulation. The future is optimization. Here is another slide that shows the same thing, and it shows what happens to the release. It's the red line coming out of the reservoir in the very first day. It will propagate to the second river reach on the second day and the third river reach in the third day. And this is the way we will link our decision on the first day to its consequences on the third day. This is the only way we can do it. This is termed model predictive control. The term comes from Holland, and it essentially means that we are making a decision for today based on the forecast for the next 2 days. And then we're going to move the whole forecasting horizon by 1 day, and we're going to repeat the whole sequence by updating the reservoir levels and updating our forecasts. Of course, we have to develop this flood damage function downstream, which will tell the model to minimize exceedance of spills from the downstream channel. So, if you look at this as a system of having a runoff forecast model and this multiple time step optimization combined into a single package, then we have no more need for rule curves, at least not for short-term operation, because seasonal forecasts are a little harder to get. But this can be compared to automated reservoir operation. In the beginning, when we had self-driving vehicles introduced in the transportation industry, it was something of a laughable topic, but I am not the first person who thought about this. And the first paper that described this whole scheme was published in 1983. We have also this paper from 1999 from Charles Howard. The name of the conference was Preparing for the 21st Century, and the paper has a provocative title, Death to Rule Curves. The application of this was done in the Damodar River Basin, and you can see the effects of routing on the river reaches between the reservoirs. We had daily data from 1961 to 2017. 11 catastrophic floods happened in that period, and we managed to keep 9 out of them completely in check. This is one of the worst that we didn't quite keep in check by only using 2-day forecast, mind you. So here is what the solution in the left corner looks like if we have a forecast for only 1 day. If we increase the forecast for 2 days and repeat this solution process, we're going to almost completely eliminate the flood damage, and with 3 days we have no flood damage whatsoever. Keep in mind this horizontal line you see in the bottom has been obtained by effects of routing and tributaries downstream, and we're looking at 4 reservoirs operating in unison together here. We can also use this procedure in drought management. And if you look at these lines with different colors, each line is a perfect rule curve or perfect trajectory of reservoir levels for a particular year that was sold. Now, if you have enough of those years, we can do statistical analysis. These are the probability density functions that you see at the end of every week. And we can identify 50 percentile, 80 percentile, 20 percentile, and create the so-called operating zones. Now, each zone is going to be associated with a certain level of reduction in demand. So if we are above the blue line, we have no reduction. If we are between the blue line and orange line, we will reduce demand by 20% and so forth. This is only one way to optimize or to use the results of optimization based in planning studies. So far, there is no set guideline for how to create a basin management plan or basin master plan. We should actually have this, and this is where research could help. This is not the only way to use this, but there are, of course, other ways. I'm going to skip this discussion of the difference between multi-objective and multi-purpose optimization. It's interesting. We can discuss this over the break. And I'm just going to move into the last few slides that deal with our flood design. Our flood design procedure is very complicated now. You probably all know that if you have a catchment with more than 5,000 square kilometers, you have to subdivide it into smaller catchments. We're making then all sorts of assumptions which we know are not true, like, for example, the linear channel routing between the catchments. We calculate travel times based on empirical formulas. We assume even distribution of rain over the entire catchment. This is, by the way, the Hirakud Reservoir catchment, 83,400 square kilometers. We know that there's never going to be the rain of equal depth over the whole basin. And then if you look at the historical data, we don't see that the peaks are going up, they're actually going down, probably due to the effects of regulation, which is something that the current procedure is ignoring. There are easier procedures. This procedure, if you look at the solutions from 1976 to 2025, gives various results depending on who does it, even though they're all supposed to be following the same procedure. And it does make a big difference whether you have to increase the size of your spillway by 17,000 cubic meters per second or not. The model we use in Canada is much simpler. It doesn't require convolutional integrals. It is based on historical paper from Nash, published in 1957, which proved that the hydrograph shape should be a gamma function. It uses rational theory, which is essentially calculating the volume underneath this hydrograph by multiplying rainfall area and runoff coefficient. And it gives pretty good results because they are much more consistent than the current hydrometeorological approach. Now, what we want to remove from the hydrometeorological approach is the uncertainty of who does it and the variation of the results that we're getting. And the only way this can be done is by getting involved the research community to inspect a large number of alternative approaches, this being only one of them. So to recap, what we'd like to do is we'd like to, the future operation of reservoirs to be applicable to reservoir operators in terms of helping them guide their decisions. We also need to develop proper benchmark tests because at every conference I've been to, there are tons of different presentations on different papers. I'm also an associate editor for major journal, and there's been 18,000 papers published since 1960s on reservoir operation. That's a lot, and we should have some benchmarks which will distinguish the quality of those models and provide information to the operators which ones they can use. There is also significant need for data-driven runoff forecasting model. We live in an information age. We have satellite data coming from various sources. We have artificial intelligence, but we still don't have self-adaptable, self-learning forecasting model, and we should have it, and we need it badly. And this is what the research community should focus on. Finally, a simplified procedure that is more consistent and more reliable for estimating design floods is highly desirable, and I think the research community could be of great help in that regard. Thank you very much for your attention.